A clique becomes an independent set, and an independent set becomes a clique. Okay? So we can do this either way. So this is just, we complement the graph. So just every edge that's there is taken out, every edge that's absent is put in. Okay? So you should sort of see that if you have an algorithm for independent set, it gives you this means you also have an algorithm for clique. If you have an algorithm for clique, you also have an algorithm for independent set. Any questions? Reset, start. No questions? People are still here? Okay. Now, it's not quite as obvious to see that independent set reduces to vertex cover and vertex cover reduces to independent set. Okay? So we believe this, right? So you just complement the graph and instances of clique become instances of independent set. So now we say independent set reduces to vertex cover reduces to independent set. So this is also pretty easy, not quite as easy, but the key is the complement of an independent set is a vertex cover. So this is actually shouldn't be capitalized because it's not an independent set. Is a vertex cover. Right? Why is this true? Because if you take an independent set, well, there are no edges between those vertices, right? So if you take all the other vertices in the graph, all of the other edges are between those vertices. Or, well, okay, not between those vertices, but between, they have at least one endpoint in those vertices. They could have one endpoint in the independent set. Okay? So if you, in the independent, no edge goes between two vertices in the independent set, so every edge either goes between two vertices not in the independent set, or between a vertex in the independent set and a vertex that's not in the independent set. So if you take the complement of the independent set, it has to include at least one endpoint of every edge. Okay? Similarly, if you take a vertex cover and you say, okay, look at all of the things which are not in the vertex cover, they cannot have, if you take the complement of the vertex cover, there cannot be an edge between two vertices that are in the complement of the vertex cover, because otherwise that edge is not covered. Okay? So before we complemented the graph, and now what we're going to do is say, okay, GK, you say, is there an independent set of size K? Well, if this is the instance of independent set, you say, okay, is there a vertex cover of size G n minus K, where n is the number of vertices? Okay, because there is a vertex cover of size K, there's an independent set of size K, if and only if there's a vertex cover of size n minus K. I think I'm getting this right. Okay, questions? So you can see, like, and therefore, since clique reduces to independent set reduces to clique, independent set reduces to vertex cover, clique also reduces to vertex cover. Why? Because if we had an algorithm for vertex cover, and somebody gave us an instance of clique, we would turn it into an instance of independent set, and then we would turn that instance of independent set into an instance of vertex cover, and we would solve that so we would get a yes or no, and that yes or no would also be the answer for our instance of clique that we were given. Okay? So if you could solve vertex cover, you can solve clique, you can solve independent set. So all of these three problems are sort of equivalent. That is not terribly complicated, right? Okay. So now, let's see something that is a little bit trickier. We don't need this, do we? So we're going to see that a problem called 3-set. So for 3-set, for 3-set, we are given a Boolean formula in Boolean 3CNF formula. So 3CNF, CNF is conjunctive normal form. A conjunction means an and, okay? So this means is ands of ors. 3CNF means each clause has 3 variables. So it's something like x1 or not x2 or x3 and x2 or not x3 or x4 and x1 or not x3 or not x4. So this is every clause, these are called clauses, is has 3 literals, 3 variables, positive or negative. So this is a not, this is an or, this is an and so every clause has 3 literals, and it's the and of clauses, of the literals are ored together, and it's the and of the ors. Okay? So this is called 3CNF. So if we have time, we're going to see that not only is SAT NP complete, this is NP complete, and this requires something called the Satan transform. And maybe we're going to have time for that. So, if you believe me that this, you can reduce SAT to this problem, now let's see that you can reduce this problem to clique. Now, clique, independent set, vertex cover, those are all sort of graph problems. They all sort of sound the same. This is a logic problem. So it seems a bit weird that you can take this, you can solve this, if you can solve clique. So this reduces to clique. If we have an algorithm for clique, then we have an algorithm for 3-set. Okay? Now, I'm just going to show you by an example, say that we have these. So what we do is we draw a graph. How do we draw the graph? For each clause, we draw a set of vertices. So this is going to be x1, not x2, or x3. This is going to be x2, not x3, x4. And this is going to be x1, not x3, not x4. Okay, so this is actually is going to be what's called a, if you have k clauses, this is going to be a k-partite graph. We're not going to draw any, for each of these clusters, we're not going to draw any edges within the cluster. Okay, what we are going to do is draw edges between the clusters. So, in particular, we're going to draw an edge between each vertex and all of the vertices in the other clusters that are compatible with it. Okay? So, x1 is compatible with x1. If x1 is true, then x1 is true. If x1 is true, then not x3 could still be true. Those are compatible. If x1 is true, then not x4 could still be true. x4 is not compatible. Not x4 is not compatible with x4. So we don't draw this edge. We do draw this edge. We do draw this edge. Okay. So what I'm going to do, because this is going to get very, I'm going to draw the edges, I'm going to draw in red the edges which are not there. Okay. This edge is not there. Okay. So actually I'm going to take these out. Take these edges out. Now remember, the red edges are the edges we do not want. So actually, I guess what I'm doing is I'm doing a reduction from 3 set to independent set. So we draw x2, not x2 to x2, not x4 and x4, x3 and not x3. So x1, these are fine. x1 never appears anywhere else. x2 doesn't appear there. x3, it's like this. x4 and not x4. Okay. So actually, you can see why it was going to get very messy. These are the edges that are missing. Two not x. We have 2 not x3s. Yes, because we had 2 not x3s in this formula, and 1 x3. Okay, so this is actually the complement of my graph. All of the edges which are here in red, the red edges disappear, the other edges appear. Okay, it's actually, I think, easier to draw this. So maybe I'm doing a reduction to independence. Now, what I'm going to argue is, if there is, let's do independence set, changing it on the fly. If there is an independent set in this graph with the red edges of size k, oh no. No. Because then what I would also have to do is, to make this the independent set, I would have to draw each of these, which is actually not so bad. Right. I have to draw each of these. When I take the complement of the graph, these are... Okay, so now I'm going to argue, if there is an independent set of size k, where k is the number of clauses, then there is a satisfying truth assignment. Okay? So that's what we want to argue. Why is this true? Well, we can't... an independent set can't include any two vertices from the same cluster, right? Because we put all the edges in between the clusters. This is actually easier to draw than the clique thing because, okay, so we're reducing SAT, to 3 SAT to independent SAT. So we can't include anything in the same clusters. Now, if we include this vertex and this vertex, there's no edge between them, so that means they are compatible. One could be true, and the other could be true at the same time. Like x1 could be true, and not x3 could be true at the same time. Not x3 being true means that x3 is false, which x3 being false, for example, makes this clause true. So if there is an independent set of size k, it means that I have to be choosing one vertex from each of these clusters, which is choosing one literal from each clause, and they all have to be compatible. So I'm going to do this in blue. For example, if I choose this x3, then I can't choose, yeah, I can't actually choose this x3. I couldn't choose this one and this one because there's a red edge. But I couldn't choose this one and x4 and not x4. But I can choose x1 and x3 and not x3 and not x3 and x1. These are all simultaneously compatible. So I'm going to claim that if I have x1 is true, not x3 is true, and not x3 is true, x1 being true makes this whole clause true, not x3 being true makes this whole clause true, and not x3 being true makes this whole clause true. If I can't find an independent set of size k, then it means there's no way to choose a literal from each clause such that they're all true and they're all compatible. They can all be true at the same time, which means that my Boolean formula is not satisfiable. So the graph without these three thingies, without these blue edges, this graph has an independent set of size 3, if and only, 3 being the number of clauses, if and only if this formula has a satisfying truth assignment. And this works for any 3-SAT formula. Okay? So that means if we have an algorithm for independent set, then we have an algorithm for, so if we have an algorithm for independent set, then we get an algorithm for 3-SAT. And therefore, since if we have an algorithm for clique, we have an algorithm for independent set. If we have an algorithm for clique, then we also have an algorithm for 3-SAT. So you can see I need more board space. We had clique. This is, remember the map I drew at the beginning of the class, at the beginning of the course. So you have clique, you have independent set, you have vertex cover, then you have 3-SAT, and we saw that clique goes to independent set, and independent set it goes to clique, and independent set turns into vertex cover, and vertex cover turns into clique, turns into independent set, and now we've just seen that 3-SAT, we can reduce 3-SAT to clique. Okay? Could you say that again? G has an independent set of size 3 if that particular graph had an independent set of size 3, if and only if this particular formula, 3-SAT formula, has a satisfying truth assignment. Okay. So now we want to see, I'm going to show you that clique, if you can solve SAT, not 3-SAT, it's true of 3-SAT, we're going to get there. I'm going to introduce this other problem, which seems more powerful, which is SAT, which is just Boolean formulas. Given a Boolean formula, does it have a satisfying truth assignment? And now we want to see this edge, which I'll draw in red. I'm going to sketch that clique reduces to sat. And this is going to give you an idea of why Cook's theorem is true. Because sat is really powerful. You're going to see that sat is like a programming language. In fact, if you've seen Prolog, then you can believe that it really is a programming language. You have some idea of how to use logic as a programming language already. Has anybody seen Prolog? Do they teach Prolog anymore? Yes. Wow. It's still around. Okay. So if somebody gives me a graph, and so actually, sorry, we saw 3 sat to independent set. It's usually presented as 3 sat to clique. We did it as 3 sat to independent set so that I didn't have to draw all those lines and it wouldn't be so confusing. Okay, let's see clique to sat. So somebody gives you a graph G and an integer k. So we're given gk, and we're asked does G have a clique of size k? Okay, and what we want to do now, before we took a formula and we turned it into a graph, now we're going to take a graph and turn it into a graph and an integer and turn it into a formula. Now, it's not going to be a 3 sat formula because we may or may not get to Satan transform today. Okay, so how are we going to do this? Well, suppose that the vertices V equals V1 up to Vn. Okay, so now we're going to establish literals. So x1, well, xi is an indicator variable. And it's true. This is how to think about it, but we actually, like, you can't insist on this. You have to write the formula in such a way that it's satisfiable if and only if the graph has a clique of size k. But think of it as xi is true if vi is in the clique, false otherwise. Okay? So for each variable, for each vertex vi, you have this xi. Okay, so now suppose you have suppose vi, vj, this edge, is not in the graph. So suppose edge vi, vj is not in the graph. Then you can't have xi, you can't have vi and vj both in the clique, because then it's not a clique, because there, between 2 of the nodes in the clique there's a missing edge, right? So what you're going to say is not xi and xj. So you're going to have, in your formula, you're going to have something that says, if this edge isn't there, then you can't have both of these. Right? So you just go through, and oh, and the other thing, yeah, this is going to have to remember all this stuff. So you just have to go through, and yeah, I think that's enough. And then it's XOR. It's not the case that they're both true. Yes. So they can both be false. One of them can be true, one of them can be false. It's not going to work if you say, okay, if there is an edge, then they both have to be true. That's not true, because you can have an edge and one of them is in the clique, but the other one isn't. Right? The only thing you can't have is if you don't have the edge, you can't have them both in the clique. And then you have to write a formula that says you need a clique of at least size k. So you want to somehow say that if you sum up all of these xi's, that I could have just paid attention to the fire engines going past, or whatever those things are.